Good evening, all of you. Myself, Dr. Partha Pakray. I'm an associate professor at National Institute of Technology, Silchar, and I'm working in this quantum computing last 2 years, 2 to 3 years, and I started in 2022, and I got funded from Amazon US and as well as that government of India, METI, to run this project. So Amazon is offering me total 28,500 USD for credit to access the actual quantum machine. So I mostly worked on that classical quantum computing system. So, and of course that working on the Python programming and using the Python code. And last 2 years is of course that it is very difficult to understand that how to write the code in Python. So of course whatever we did in the classical, so it's very difficult to understand how to write the code and what will be the qubits, how much we can take it. So it's very difficult to do that one. But now we of course that to overcome this particular part. And I will show you that that some of the codes in the Jupyter, of course not Jupyter Notebook, also in the Google Colab. So and some of the fragment of that code, like how we can implemented that particular part. So of course that I'm not going into the deeper. So of course the some of the important terms are there, like one is the simulator. Simulator is the most of the important tool for this quantum, because the original quantum system is very expensive. Like I'm using in the like Amazon Quantum services through the cloud. So last 2 weeks back, I started with the experiment, and suddenly one code ran that particular system, and within 10 minutes, it cut 1,300 USD. So now you understand that how much cost it is. So it's very expensive for that one. So before running to that direct like quantum system, so of course you have to run first in the simulator, and if the simulator is okay, then we can directly call the system and then quantum system, and then we can do that part. So there are various simulators are available. Like one is of course that IBM developed that one, Qiskit. So everyone using that one. Another one is called the Pennylen. So basically for that Qiskit, you can use for any of the applications. Any of the applications means like you can use for the machine learning, you can use for that like optimization. So any of the applications, so you can use for this Qiskit and this particular simulator. Another one is called the Pennylen. Pennylen is basically for fully developed by the machine learning tool, machine learning like applications. So it is only for using any of the machine learning cases. So we can use for that one. So of course, then I can show you some of the hello world kind of code. So of course, every programming language, of course, we know that how to write this basic code that you can access for that one. And that I'm not going to discuss in the Qiskit. So only one code I can show you in the Pennylen how to do that part. Okay, so the most important part is the quantum computer. So these are the various types of that one, like superconducting trapped ion qubits, and of course the quantum dots. And another one is called the photons and the neutral atoms. So of course that superconducting, you can see these. So you can see that part, Google, IBM, and Rigetti. So these are the based on the superconducting materials, that they are operating extremely low temperature, and trapped ion qubits, like that is also using some of the companies like IonQ, Alpine, Quantum. So this technology they are using. And the quantum dot, there are some of the companies they implemented that one, direct and the sequence and then quantum motion. And then you can see that photons also like light particle used to send the quantum information. So some of the companies also associated with that one, and neutral atoms also, like Pascal, you know that in the French company, so that they are using for that one atom computing also. So they are using these neutral atoms for that one. Okay, so these are the things, and the most important thing, of course, whenever we deal with these things, qubit and the quantum gate and the measurement. So these three part of that, of course, the most important component for that one. And of course that we can see later on, I can explain for that particular part. So you can see this. First of all, I can discuss a little bit about the Qiskit, and then we can go for that penny lens. So of course that Qiskit is an open source quantum computing software development kit. So before starting your code, so you can download these tools, and then you can run your own quantum computing programming. So there is no real machine is required for that one. Okay, so that is developed by, of course, that IBM, and there are some of the key features are there, like quantum circuit simulations, quantum hardware access, and the classical quantum hybrid computation. So now, whatever the paper in the natural language processing, so most of the cases, like 100%, we can say, like most of the cases, they are using the classical quantum system. So they are try to implement that whatever the applications are there. So they are trying to build a classical quantum system, basically for the some of the part. Okay, so we can see there are various history are there, but I am not going to that part because component of this Qiskit. So you can see that basically it is using for the basic component quantum circuit, quantum register, and the classical register. So it is using for that. And of course that there are some workflow also there creating quantum circuit. So of course that whenever you build that one, you have to build some of the quantum circuit and then compiling this quantum circuit. And once it compile, then you have to run these things first. You can run in the simulator, and once it succeed, if you think that okay, it is okay for that, then you can just give it to that real computer system. Okay, so this is the Qiskit platform. So of course that another one is the penny lens. So you can see this penny lens is basically only for the integration of these machine learning tools. Okay, so most of the cases, so it is using the quantum classical application, it used for that. Okay, so of course I can show you something on that one. So I can show you some Amazon cloud system. So you can see this thing. Then I'll explain that part. So this is the Amazon bracket service. Actually, they are providing the services for that one, and we can go for the devices. Now you can see this kind of devices available for that one, and that first three things you can see mostly that can use for the simulator. Like you can see that it is providing 34 qubits, 50 qubits, and the 17 qubits for the first three, and rest you can see like IonQ and the IQM and the QERA and Rigetti. So they are providing for the quantum cloud services. So if you connect to that one, some of them are, you can see the reservation only. So it is very, very expensive. So you can see if I open this particular part, and then you can see that. So you can see the cost is associated here. So you can see that per hour cost is 3,000 USD for that one, which is very, very expensive for that one. And of course this availability time also you have that one. So you know that if you run your code, so you have to check your time, and then you can run that particular code. And of course that particular location is, you can see that Finland is located for that services for this part. So of course that every quantum services is very, very expensive. So of course that higher qubits, you can see the QERA is that very, very higher system. So you can see it is, of course it is also the same price for that one. Now so this is the devices that we can use for that. Okay, so of course that before writing any code, so of course we have to start with some of the creating the circuit. So of course you can see that previously we had discussed some of the gates are there, and poly X, poly Y. So and then finally you can see that measurement. Of course there is a measurement part also there. So you can use for that particular code for creating the quantum circuit. And then once you've done that one, then you have to create the devices. So you can see that whenever we can say like device dev1 equal to that particular device, this is only for your local machine. So qml.device, and inside that lighting.qubit, this is particular only for your local machine. But whenever you want to give that actual machine, like if you want to run for that one, so in that case you have to go to that just put the path of that particular quantum machine. Suppose I want to use for this IonQ quantum services to my machine, so how we can connect it at that one? So we have to give this device path of that one. So if we give the device path of that one, so it directly connect to that quantum machine. Of course, not from your local machine, because you have to call for the API. And if you want to go for that actual machine, so of course you have to run through the simulator through the Amazon. So first you run your own code in your local simulator. Once it's done, then you have to put into the simulator in Pennylen. It is also involved in this particular devices. If you go for the devices, and then you can select this particular simulator. You can create that one, and of course you can create also the first notebook. And once you create the notebook, and you can run the code for here, and then of course that particular link of that Amazon services, so then it can directly run to that part. Okay, so now this is the QML devices, and then constructing the Q node. So Q node also you have to constructing the two-way. Q node is basically the quantum circuit in the multiple quantum devices. So you can see that multiple quantum devices, how to create. So there are the two way you can create for that one. One, you directly give it to that path, and then and second way of that one, you can create like this way, or you can use this particular way to do that part. And once you've done that one quantum circuit, so then you have to you can give some values for that one, and then you can draw this circuit, and you can draw this particular circuit if you want to see that one. And then then you have to calculate the quantum gradients for that one. So now one of my students, so he's of course working in this domain, so he will show you that each of the fragments, so how we can create that classical part first, and then how to run in the quantum, and then finally we can get the result. So I can ask that Mr. Sambabu is present here.
Yes, sir.
Yes. So can you share your screen for this Google Colab part?
Okay.
So he will explain for that some of the fragments of the code, so how we can run for sentiment analysis. Previous experts is talk about the sentiment analysis. As you know, the sentiment analysis we can classify for like either positive sentiment, or the negative sentiment, or the neutral sentiment. So this code, so he will explain like first how we can build in the classical, then how we can run in that quantum, and then finally once we get the result, and then finally we can show the result, sentiment classification part. Okay, so Sambavu, you can share your screen.
Yes, sir. May I first show the hello world first, then I go for the hybrid quantum neural network?
No, so that code, particular sentiment analysis code, you can explain. You can share in that Google Colab. So it will explain like 10 minutes, so maximum 10 minutes to explain that code.
Good afternoon, everyone. I am Shyam Babu Pandey, a PhD scholar under the Dr. Partha Pakray. So here I am giving one demonstration of how can you construct the hybrid quantum classical recurrent neural network to perform the sentiment analysis. So first we by using Pennylen. So first we have to install the Pennylen, updated Pennylen. So this is the code how you can install the Pennylen. So here we are performing the sentiment analysis on the Hindi dataset. So for that we need to next install where we are installing the Indic NLP library, which provides the different functionality to pre-process the dataset. Next we are here importing the different required library such as Pennylen to construct the quantum circuits, NumPy to apply the numerical operations, Torch to create the neural networks, and linear to cross entropy as a loss function, and pandas to perform on the CSV file. Next, here we are loading the data set, and this is here we so this is the first 5 data sets. So this data set has written in the Hindi, and this data set has 2 levels, one for positive, another one for the negative. So one represent here as a positive, and 0 represent as a negative. So after loading the data set, we are performing the pre-processing of the data set, like removing the stop words and identifying the unique words in the data sets. So total words are 14 1300, and total unique words are 838. And this is the stop words which we are going to remove from the data set. Now we create the vocabulary. So in vocabulary, where we count the each unique words, and we are map the each words with integers, and convert the sequences into the integer IDs. Yeah, so this is the one of the sentences where we convert the sentences into the integer ID. Now next, we are fixing the length of each sentences as a sequence length of 10. So if sentence length is shorter, then it will be padded by 0, and if it is longer, then truncate into the sequence length into 10. After we to train the model and evaluate the model on the test dataset, we splitting the dataset into the train and test. So total train set is 253, and test data is 45 sentences. Now we convert data sets into the tensors frame, because PyTorch operates on tensor. So we are converting the data set into tensor format, and this is the quantum circuit which we are going to define. So here we are defining this quantum circuit. So first part is for the data encoding. Whatever the classical data will come, so first we need to encode the data, because quantum computer does not understand the classical data, so we need to convert into the quantum states. So to converting the quantum, here we are using angle encoding, where each data features of each data point is encoded into the rotational angle of quantum circuit. And next we are using the these are the parameters which are used during the training of the quantum circuits. And after that, this is the entanglement layer, which generates the entanglement between the different qubits. So here we are using total 6 qubits, and finally we are measuring this circuit to generates the classical outcome of the quantum circuits. So this is the how can you create the quantum circuits. So this is the diagram of which quantum circuit we have created, and this is the how can you create the quantum circuits. So this is the Python code to create the quantum circuits. So first we are defining the quantum number of qubits. Here number of qubits are 6, and next we are creating the device. So a device is maybe a quantum circuit, maybe a quantum computer, or maybe a quantum simulator. So here we are using a local simulator, like that name is default simulators, that is provided by Pennyland. And next we have to define the number of qubits. So here which is assigned into the wires. After that we have to declare the quantum node. So there are 2 ways to define the quantum node, as sir told. So first one is by the constructor, and next one is by the decorator. So here we are defining by the decorator. So basically quantum nodes uh, behaves like an intermediator between the quantum devices and quantum circuits. So here it is encapsulated with the name of the quantum devices, and then we define the quantum circuits. In quantum circuits, first we are first part for the declaring the angle encoding, which is given in the diagram. This is the first part where you are using the angle encoding, and next is creating the basic entanglement layer, which contains a single qubit rotational gate and the native entanglement layer. And finally, we indicate the weights of the quantum circuits. Here we are constructing this quantum circuit into the 4 layers. So total parameters is for the quantum circuit is 6 total number of qubit rotational, and 4 layers for each layer contain the 6 quantum circuits, and there are 4 layers. So total 24 parameters here we are defining. Now we are creating the hybrid quantum classical neural network. So it combines the some part from the classical and some part from the quantum. So here this is first we are constructing the embedding layer, which convert the data set into the word embedding. Next we are using one classical linear layer to process the data. After that we are constructing the uh, quantum layer to further process the data, and finally we use a classical linear layer to give the outcome of the neural networks. So I can show the so this is the diagram of hybrid quantum classical layer. So first layer is we are using embedding layer, which converts the data into the word embedding layer. And then we are using linear layer to process the data. This is classical layer. Then after that we are using the quantum circuit as a quantum layer to further process. Finally, we are using classical layer to extract the output from the this hybrid classical neural network. Next, we are defining the hyperparameters of the model, like vocab size, output size, embedding dimensions. Here here we are just our main goal to demonstrate. So we are taking very low embedding dimensions, and next we are defining the learning rate, and we are using here classical optimizer, stochastic gradient optimizer, and finally we define the training function, which for the train the model and minimize the cost function by the iteratively update the model's parameters. And now we run the hybrid quantum neural network for the training. It takes few times to train the model. It display the training loss and accuracy.
Hello, I have a question. On your when you're using your model, what will be the major difference between using the model without the hybrid system and going only in the part of GP learning? Is it getting a major difference, or you be like only improvements some points?
So first we are using embedding layer to convert words into the word embedding vectors. Then we are using linear layer to process the data, and we are using a quantum layer to further processing the data, and finally we are using a linear layer to get the output of hybrid neural network.
No. Question is that why we go for directly first embedded layer in the classical? Why not directly go for the quantum?
First, sir, actually, we need if we have large dimensional embedding data set. here we are using only 8. Suppose if we are using large dimensional data sets, so we need a classical layer to process that data and squeeze into the smaller dimensional data set, so that we can process with the quantum recurrent neural network. Basically, the problem is here. Right now, quantum circuits are not able to handle the large dimensional data sets, so that we need one linear layer to squeeze that data to large dimensional data set into the a lower dimensional data set, so that we can process by the quantum circuit.
Okay, so we are working on basically last 2-3 years on only that part of space tagging. Part of space tagging, like we are working on the hidden Markov model. So we are trying to convert into the hidden Markov.
Long live India and France friendship.